Okay, let's continue. We have been looking at the two-stage Miller compensated op-amp, and in the last class we looked at the circuit implementation. So again, the only point I want to emphasize from the last class discussion is, for an op-amp, it is essential that you have a DC negative feedback around it, and only the DC negative feedback around the op-amp is supposed to set the operating points. Only then the transistors will all be in saturation and op-amp will behave like an op-amp. Okay, that was the major takeaway I want you to have. So let's continue the two-stage Miller op-amp. So let me redraw this again. Additional thing. Okay. So this is the compensation capacitor CC. Cool. So here the basic idea was to try to keep the open loop poles far apart, and that we kind of accomplished by putting this capacitor CC in feedback. Now in this process, did we introduce something else? Yeah, the RHP0 tagged along as an uninvited guest, and it has been there for a long time, so people have figured ways to get rid of that. And today we look at a couple of such commonly used techniques. Okay. And for that, first let's understand why the zero is coming about. So again, remember, for zeros to occur, you need to have currents or voltages with different frequency dependencies getting added. Here you see that we have a current through the capacitor here, and one current through the transconductor, and both of these can flow from the input, and these two will have different frequency dependence, and they will add up to 0. So let's try to calculate the zero location again to get better understanding. So as usual, I'll do the following. I'll assume the output in the Laplace domain is 0, right? And let me call this current as I1, this voltage as V1, right? Now if I apply KCL at the output side, I'll have the capacitor current plus the transconductor current, both of them to be summed up to 0. Now if I call this current as I1, what can you say about the current through the capacitor? If this is I1, what can you say about this current? I1. So I'll write it directly. The capacitor current is I1 of S. Fine. And if this voltage is V1, what can you say about the transconductor current? I mean, if this voltage is V1, what is this current? Is this fine? Minus GM2 V1 of S. Sum of these two 0. Fine. Now V1 is the voltage across this capacitor as of now. Current flowing here is I1. So then what can you say about V1 of S? I have a current I1 flowing through the capacitor. So what is the voltage across the capacitor? I1 of S by SCC. Is this fine? V1 is the voltage across the capacitor, right? Because this end is 0. Okay. So I can substitute for V1 here. So this is I1 of S. Let me GM2 times I1 of S by SCC. Sum of these two 0. So again, we can prove that I1 cannot be 0 because I1 is a current getting pushed by the transconductor. If we have non-zero input, the current will also be non-zero. So the only possibility is to have S to take this value of plus GM2 by CC. Again, we are recalculating the same thing but in a slightly different way. That's it. So this is the RHP0. So now we know this guy is not something that we want, right? So ideally you don't want this RHP0 at all, right? So which means theoretically, where do you want the 0 to be located at? We don't want this at all, right? So which means theoretically, what is the value? Infinite, right? So let me actually copy this. So what we want is the following. We want the 0 to be at infinity, right? Which means that if I assume the output in the Laplace domain to be 0 and try to write KCL equations, that equation should be satisfied for what value of S? Infinity. If my 0 is at infinity, this should be satisfied only for s tends to infinity. As of now, this will not get satisfied for s tends to infinity. Correct? So how should this equation change, at least mathematically, so that this gets satisfied for s tending to infinity? Well, I mean, GM2 is not, you cannot change, right? I mean, they are design parameters. I mean, if I tend s to infinity, this term goes to 0. Only this term seems to be the problem, right? So in principle, if I don't have this term, equation gets satisfied. Okay, is this clear? But of course, I1 is not something you can make 0 because that is the current getting pushed by the transconductor, right? So we cannot touch this fellow, but maybe we can change the current flowing out of the transconductor by changing the voltage V1 so that this equation gets satisfied, right? So let us say I cannot change anything to I1. How should this equation change here so that this becomes equal to 0? What should be the term that should be introduced here so that this gets satisfied? If I somehow have minus I1 of s, now it is clear. If I tend s to infinity, this gets satisfied. We have a 0 at infinity. And remember, this is the current flowing out of the transconductor, correct? And current flowing out of the transconductor is GM2 times V1 of s. So this is the current flowing out of the transconductor. So let's try to find what is V1 of s. For that, I'll take GM2 outside here. So I have I1 of s by SCC plus what do I have? If I take GM2 common, what do I have here? I mean, I'm just taking I'm pulling out GM2 from the two terms. First term is this. What should be the second term? By GM2. So again, now you see that I have GM2 times V1 of s, GM2 times V1 of s. If I ensure that the voltage V1 is this value, we are set. Is that okay? As of now, the voltage V1 is I1 by SCC, but now I want this to be I1 by SCC plus I1 of s by GM2. Is this okay? So in this circuit, the voltage V1 is generated as the voltage across the capacitor, which is this fellow. But I want my V1 to be obtained as this. This is essentially the voltage across a capacitor plus voltage across what? A resistor with a value 1 by GM2. So what should I change here so that my V1 is obtained as this? Series or parallel? Series. I mean, sum of the two voltages, you put two voltages in series to add them up. So all I'll do is the following. In addition to the capacitor, I'll add a resistor. I'll call it RC, and this value should be equal to 1 by GM2. Okay. If I do that, now you see that the current I1 is flowing through this branch. The voltage is V1, that is sum of the two voltages. And if you ensure that V1 is of this form, then the equation will get satisfied only for s tending to infinity, meaning that you have pushed the RHP 0 to infinity. Is that clear? So let me take it to next page. So this is one easy way to kind of eliminate the RHP 0. The idea is to just introduce an additional resistor RC whose value is 1 by GM2 in series with your compensation capacitor, and that's it. So now if you think about it, when I didn't have RC, when RC was 0, where was the 0 located at? Where was the 0 at? Yeah, it was in RHP, right? GM2 by CC, exactly. So that is in RHP, right? So now I kept increasing RC, and let's say I made it equal to 1 by GM2. Where did the 0 go to? Infinity. So that begs the question, if I keep increasing RC further, what do you think will happen to the 0? So think of it like this. This is the S plane. Earlier my 0 was in the RHP. I kept increasing the resistor value. This fellow started to shift this way and went to infinity. Now if I increase it further, logically what do you think might happen? It's at infinity already, so if you increase it further, what do you think might happen? I mean, we are going this way, so what do you think might happen later? Huh? Yeah, I mean, it turns out it actually comes to LHP. Okay, and in fact, we can work out the same calculation we did. You can assume that the resistor is some RC instead of 1 by GM2 and find out what is the 0 location, right? The same thing, equate it to 0. Assume that the resistor is not 1 by GM2 but some RC. You will find that the 0 location will be, let me write it, the 0 will be 1 by GM2 minus RC times CC. So as you see, if the value RC is chosen to be 1 by GM2, the 0 is pushed to infinity. If you choose a value greater than 1 by GM2, this actually enters the left half plane. And LHP 0 is good or bad? Good. So that begs the question, why can't I keep doing this further and further and get more benefits? But for that, let's actually look at this poles also, because we have only looked at zeros as of now. So this is the 0. So let's also quickly look at what happens to the poles. So here, how many poles do you think we might have? One, two, three, four. How much? I can initialize the voltage across this capacitor, as well as this. No contradiction. So we'll have 3 poles actually. So again, to find the exact pole location, you have to find the denominator polynomial. You'll get a cubic equation, and to get the pole, you can assume that the poles are far apart, and you can take the ratios of polynomial coefficients and get the pole locations. If you do that, you will find that the first 2 poles are roughly in the same location. Again, very roughly they will be at the same location as before. And the third pole will be at this location, which is 1 by RC into series combination of C1, CC and CL prime. I can just give you a very qualitative feel for why is this the case. So let's say now first we are looking at the first 2 poles. Let's assume that the frequency for these 2 poles is such that when I have CC and RC in series, the impedance of this is larger than the resistor impedance. So we can as though consider that this is not existent. So for relatively low frequencies, not very low frequencies, low to let us say medium frequencies, this is the case. So the first 2 poles are same as before because this fellow is not playing a role. Okay. Again, this is very qualitative explanation. Now when you look at high frequencies, the current, let us say, is pushed by the transconductor. At high frequencies, where will this current flow? Through the resistor or the capacitor? So at high frequencies, only the capacitors will be active, right? So loosely speaking, we can redraw the circuit this way. I have C1, I have CC, I have RC. At high frequencies, only the capacitors will be active. So you can say that we just have this loop active in the circuit. So here you can see the 3 capacitors are in series and you have a resistor RC. So that this is a very rough explanation. Okay. So that's why you have this, right? And how can you further approximate this as? I have 3 capacitors. Which is the smallest capacitor in this? C1, right? So how can you approximate this further as? 1 by RC into This is assuming C1 is smaller than Cc and C. So let me just summarize what we have seen. Yeah. Good point. We'll come to that. We'll exactly answer this now. So first let me write down the results we have so far. So first let me write this. So earlier, let us say when I didn't have both R and C, how many poles we had? And where were the poles? G1 by C1 and GL prime by CL prime. Then we did the following. We didn't have RC, but we just had CC, correct? In this case, how many poles were there? 2 poles and one RHP 0. Quickly tell me the low frequency pole. What is the low frequency pole here when I don't have RC? G1 by, let's say C1 is smaller, CC times GM2 by GL prime. Again, this is assuming that this term is greater than 1, otherwise we have to take it exactly. And what is the high frequency pole? You just did the quiz, right? What is the GM2 by CL? Again, this is assuming you have GM2 to be greater than GL prime, and my C1 is smaller than CC and CL, and C2 is smaller than CL, right? Under these assumptions, you can write the second pole like this, and you had the RHP 0, GM2 by CC. Now what we did, we wanted to make sure the RHP 0 moves to infinity. So this is now with RC and CC. So here I've already told that the first 2 poles are roughly at the same location, no change. Instead I have a third pole that is roughly at 1 by RC C1. And the 0 actually moves to this frequency 1 by GM2 minus RC times CC, correct? So now let's come to his question. I'll answer it first by considering the 0 location. Now look at the 0 here. So here if I choose RC to be 1 by GM2, the 0 moves to infinity. Looks like we have gotten rid of the RHP 0, right? But at this point is where you should think of this, right? Earlier I had 2 poles and one RHP 0. Now I wanted to eliminate the RHP 0. I definitely did that. But in that process, did I introduce something else? I introduced a third pole. So do you think I am doing any better, or I am doing the same as before? Because earlier also these 3 contributed to phase lag. Now also I have these 3 will contributing to the same phase lag. So are we doing any better, or we are doing okay? No. Basically, if you have a RHP 0 or a pole, left half plane pole, both will add to a phase lag, right? And the phase margin reduces, correct? My question is, are we doing any better than this case, or we are still the same? Yeah, now it depends on whether the P3 is at a higher frequency than your old RHP 0, correct? We can quickly check. My old RHP 0, where was it at? GM2 by CC. Now my new third pole, it's roughly at GM2 by C1. RC is 1 by GM2, GM2 by C1. So now tell me which is, C1 is much smaller than CC. So my third pole will be at a sufficiently larger frequency. Okay, so you don't have to worry about it. Technically, most cases you don't have to worry about it. So again, now let's say I keep increasing RC now. That is, RC is greater than 1 by GM2. So if I do this, where does the 0 enter? Left half plane. And left half plane is good. So one might even consider doing the following. You can choose a large enough value for RC so that the 0 enters left half plane and exactly cancels your second pole. That is also possible, right? But if I keep increasing RC by a lot, what else can change? You see that P3 depends on RC. If I keep increasing the resistor value, this pole which you assume to be at a larger frequency will start coming to a lower and lower frequency. That will start degrading your phase margin. So you can't go crazy on this. So there is a limit to it. Best way is to keep it to be 1 by GM2, you are safe. Slightly higher is okay. But if you keep increasing it further, you will end up with the risk of the third pole actually coming to a lower frequency and affecting your phase margin. Okay. So I'll mark it here. So which means P3 reduces. I'll say phase margin. It's a question mark. And limiting case is where you have RC to be infinity, right? If RC is infinity, this fellow is not there, this branch is not there at all. So you're back to square one like this. Okay. This is okay? So this is one common way in which you tackle this RHP 0 by adding a series resistor. Yes.
Why did you connect the output of GM1 to negative terminal of the second?
So you're saying why can't I have this one, right? Yeah. Any answers for that? Yeah. Remember that this GM is going to be a single stage GM. That is, it takes a single input, single output. Simplest realization is common source. Common source, the gain is positive or negative.
So that is fine, but then
yeah.
If we don't use the common source, then we will not get a positive or 0.
Okay, he is saying if you don't use common source, okay, I understand. Very good question. So which means, let us say you have some other circuitry which gives positive gain. Why don't you do this? This was a question I gave in the practice set. Right? So please check it. Okay. Right. So you think about it. If you have doubts, let me know. This was a question I particularly gave for you to work out.